Good. So my name is Jiapan Wang, and I will represent the 4D-Works team to give the presentation. And we are the remote sensing application groups at TU Munich. And I will introduce our NFDI4Earth Pilot project 4D-Works. And our major objective is to developing the standardized metadata for the 3D time series workflows. And as a hint here, you can already see as we are working, our daily data we are working on is point clouds, but over the time, so we have a lot of point cloud files and also together with many metadata along with the point cloud and also additional supplementary data regarding the survey or collections. So it's a challenge for us to efficiently manage and reuse and also sharing this data. So that's bring us to the motivation. So nowadays we are seeing the massive increase in the very high frequency Earth observation, especially for our topographic analysis, such as a lot of sensors, a lot of data from multiple sensors like the permanent laser scanner, UAV photogrammetry, UAV laser scanner, and also the satellite images. And as a plot show, at each time where we have a lot of 3D data, and together with many metadata. But when we want to manage the data over the time, it's getting challenged because at each time maybe we don't have a standardized metadata format, and we don't have the relations between the different time epochs, so making it harder to reuse and share the data. So now we want to move from this empirical data management to the FAIR principles, primarily focusing on the reusability and the interoperability of the 4D data. And here I want to show this real world example on the right side. This is a point cloud time series data. You can see there are a lot of metadata scattered from a lot of text files, PDFs, and also a lot of time-dependent data together with the point cloud files. And the lack of this standardized time-dependent metadata actually is a major bottleneck for achieving the FAIR data principles. So to address this gap, our pilot aim to advance the research data management specifically for the 4D data. We want to extend the current 3D data standards to involve the time dimension. And also we want to develop an automatic metadata curation workflow so the researchers can compile their data and extract the metadata automatically. And lastly, we want to apply this workflow and metadata schema to the real world data sets and provide a guide and roadmap for the broader Earth system science community. And our solution is, as you show here, maybe I move this here. Okay, so our solution, as you see, it's this three-layer architecture for the metadata curation using the stack. Stack is the full name is a spatial temporal asset catalog, which is a very established metadata management tool for satellite imagery. So we want to leverage the ability and the toolkits from the stack to develop our 4D data sets. First, we have the metadata layers. We identify the important categories for topographic change analysis, and also including the common data, the acquisition metadata, processing metadata, asset metadata, and the most important, the new addition is the time-dependent metadata. And then the core contribution is this Top4D extension. We provide the JSON schema and the toolkits to help user to build and validate the metadata from the raw data. And finally, when users can build such a metadata structure, it can be used. They can output the stack items and catalogs, allowing for the efficient search and usage. And then I will go through these three layers to give you a more detailed description. So the first active step is metadata harvesting. So we take a very diverse unstructured metadata from the different sources, whether from the satellite image, UAV, or terrestrial laser scanner, and over the multiple timestamps, and harmonize them into a unified key value dictionary. And what could this metadata be collected from? It's first, there are some common data, mostly the descriptive and the administrative data sets like identification, license, and platforms we used for this specific acquisition. And then we have some acquisition related data, mainly related to the sensors we used, how we acquire the data, how we measure the data, and what's the accuracy of this one timestamps. And then we have some processing related data, like when we collect data, how we process them, what's the data quality, what's the data products. And very importantly, when we acquire the data, from time to time, we have the alignment over the time and also transformation, reference epochs, those time-dependent metadata. And last is actually data links and also the menus to the additional supplementary data. Those are the assets data metadata we want to include it into this. So we harvesting all of this diverse metadata source into a unified dictionary to support our next automatic metadata transformation workflow. So in the second step, we transform this unified metadata dictionary to a stack items. And based on our proposed Topo 4D extension, you can see that we can create such a GeoJSON file, including the new extension and also the additional metadata as properties. And additionally, we also provide a user-friendly web form, which is open, which can be used for the non-programmers, which allows to just upload the point cloud files and create metadata stack items. And from both of these tools, we can get a GeoJSON, which is also a stack format for the stack items. It's a standardized metadata for our data. And when the users or the researchers, they have multiple items from different sources, different times, it's possible to assemble all of these individual atomic stack items to integrate into groups them into collections or the catalogs. For example, I show an example of a multi-source, multi-temporal catalog. This catalog integrates the planet scope imageries and also point clouds from UAV photogrammetry and also the derived change point clouds into one unified time length. And with these catalogs, users can use Python or any tools, just load the metadata and can make such a plot and explore where the data is and when the data was acquired. And further processing or additional metadata can also be easily retrieved from the GeoJSON files. And secondly, second example is we curated a subset of near continuous 4D point clouds. For example, this is a 1 month 3D time series of a Kagdon data set. It's a point cloud time series collected from the Netherlands. And we can see all of there are about 1,000 point clouds grouped into this collection, and just using the catalog and the stack browser, users can check the metadata of each items or the overall metadata regarding these collections. So these hierarchical structures can become the main entry point for 4D data. It can allow the users and also the systems to easily search, filter, and visualize the data sets across the spatial, temporal, or even semantic dimensions. And they don't have to inspect every single files and just looking through these catalogs. And so as a record, this three-layer architecture can allow us to collect the diverse metadata from the source and transform them into the standardized formats, which can be integrated into Stack and provide us a very simple entry point to use the metadata. And so how we can use this and access this? So we provide our deliverables and also our contributions to the community. First is this topographic 4D extension specifications, which is a JSON schema officially proposed and hosted on GitHub, so users can use and retrieved by the identifiers or via the GitHub repository. And secondly, we provide these two example catalogs together with the extension, so users can know what this catalog can do and what the extension can do. And this metadata form also is usable and hostable on any virtual machine or servers. And also we provide a comprehensive guide and Jupyter notebooks to demonstrate how to build the stack catalogs from the scratch and the APIs, what APIs we can use and what further steps we can do. And also, of course, the roadmap we have submitted to on the node, which it's a set and entry point for the NFDI4Earth and Earth Science System community. And furthermore, we disseminate these contributions to scientific contributions, including a full paper submission and also half-day tutorials in the upcoming ISPRS Congress. This is also a major community for the users and people who are interested into this data and the analysis. And to summarize, we tackle the major challenge of the lack of the standardized 3D times metadata by developing an automated curation workflows and the Topo4D stack extension. And this makes a very complex multi-source, multi-temporal 3D data align with the FIRE principles, especially regarding the reusability and the interoperability. And looking ahead, our future direction could be enhancing the integration with the open source processing tools and establishing the catalog hosting servers for the 4D topographic data sets. And in the end, we want to move towards an end-to-end research data management workflow from the data acquisition straight to the analysis. And yes, that's all. Thank you for very much for your attention. I'd like to acknowledge the entire 4D-Works teams and the support from the NFDI4Earth program. And the last is a little advertisement. If you plan to participate in the Congress in July, you are very welcome to join our half-day tutorial session and to get some hands-on practice how to handle the 4D topographic data and how to use them. Thank you.